Thank you very much, Pamela. Hello to everybody here from Leoben in Austria. So let us go directly into the topic again. As Pamela mentioned, fatigue is an important aspect in many engineering applications of polymers. And maybe let me also make one comment to the talk of Luca Antena about environmental stress cracking. So from my point of view, and also what you see in literature, environmental stress cracking and fatigue may be the most important and the most critical aspects when we talk about failure of engineering applications of components in polymers in the real service world. So the goal of my presentation today, fatigue in polymers, is more or less to give you a broad background to fatigue, quite quickly, of course, and in the follow-up presentation of Andy Brunner and his colleague, he will go more deeper into the aspects of fatigue in composites using fracture mechanic aspects. In the presentation from me, also conventional aspects of fatigue will be covered. And so therefore, I want to also go now very quickly into the topic, why is fatigue of polymeric materials so important? So if you look into many engineering applications, you see that fatigue, of course, is a very relevant topic, not only in aircrafts, of course, but for example, as you see here, the second component is an air intake manifold in the automotive industry with short fiber reinforced plastics, but also in polymeric materials, polymeric components like a pipe. Also, fatigue is an important aspect because you see here the situation, if you have traffic loads under a buried pipe of course, you do not only have internal pressure, but also, of course, fatigue loads on the pipe. So why is fatigue so important and so critical to consider? And that can be easily explained by the following diagram. So what you see here, if we have a conventional monotonic load, so we take a specimen or a component loaded under a defined deformation rate, typically we find then a maximum stress. And this maximum stress is you can see here in the diagram now, failure stress over time to failure. If we apply now a long-term static loading, kind of creep loading, what we typically find in polymers and viscoelastic materials is that this failure stress is decreasing over time because of viscoelasticity in the polymer. However, if we use fatigue loads, we even see a much stronger decrease in the failure stress over time, so over cycle numbers, because in addition, we also have damage that is developing in the material, and this leads to a further decrease of the failure stress. So therefore, fatigue is so important to handle with, and if engineers or design engineers do not cover this aspect, that the maximum stress that the component can survive is decreasing over time, over cycle number, this, of course, then can be the reason that sometimes components fail quite surprisingly. So, and as already mentioned, of course, we see a lot of failure in polymers, in fiber reinforced polymers as a result of fatigue load. Here, even a failure case we dealt with in the last years, where we looked at the PET beverage bottle, where fatigue failure was a result of different temperatures, overnight temperatures in the storage rooms. Here you can see a typical fatigue fracture surface of a short fiber reinforced polypropylene, and here carbon fiber reinforced composite laminate. It's a typical specimen failing under fatigue. So that is a kind of introduction. I will go now directly into the situation of fatigue. So when we talk about fatigue in polymers, we have to see the situation that as a result of the viscoelastic behavior of polymers, we have the situation that if you load now a polymer here with under stress control, for example, you typically have a shift in the reaction of the polymer. And this time shift here, then in the strains that we can measure, is the reason that we have to deal here also with two moduli in the evaluation. We have the so-called storage modulus and we have the loss modulus. And the tangent theta is the loss factor. That is the relation between the loss modulus and the storage modulus. So it's a bit more complicated aspects we have to deal with in fatigue. So if we do now plot stress over strain as a function of cycle number, we measure typically in viscoelastic polymers a hysteresis, as you can see here. You can see here stress over strain, and here the hysteresis. And here the loss work, so the work that cannot be recovered, is the area within the hysteresis. And we have the recoverable work, that is the yellow area here below the hysteresis. And as a result of this, of the lost energy in a fatigue test, we have to deal with hysteretic heat up of the polymer and of the specimen. And this also have to be considered if you are doing fatigue test. And in many polymers, it is not possible to do the tests at very high frequencies, because if you increase the frequency, then it's you see here the equation that describes the hysteretic heat up rate, and also here an equation for the hysteretic temperature rise. And you see here the temperature rise is dependent on the frequency. Specifically also on the stress range, the stress amplitude, even to the power of low, so it's even more important. And you see here material parameters, like the specific heat or the density of the material, but specifically also the loss compliance. So then the loss compliance typically is very high in the region of the glass transition temperature then of the polymers. So you have to specifically be very careful if you are testing polymers in fatigue, if you are testing at the temperature that is around the glass transition temperature. There you typically then have a lot of hysteretic heat up in the material. So, for example, if you're testing a polyethylene material with a glass transition below 0 degrees Celsius, and for example, on polyamide materials, where the glass transition typically is in the range of room temperature or a little bit above, typically, therefore, you have a much higher temperature increase if you test polyamide 6, polyamide 6,6 materials in comparison to polyethylene. So in testing, of course, you have to consider this and to test polyamide at much lower frequencies than, for example, that you can use for polyethylene. So this is a very important aspect in dealing with fatigue. If you're doing fatigue tests, please always check the temperature development at the specimen directly. It can be done quite easily with infrared sensors, for example, so that you get a direct feedback if there is a temperature increase at the specimen or in the component. So if we talk now about fatigue, we can use two different ways to evaluate the results. On the one hand, we can use the typical stress-based approach that is used over years, and we can look at the fracture mechanics approach. In my talk, I even will focus a bit on the stress-based approach, because then following up, Andy Brunner specifically will then talk about the fracture mechanics approach in composites definitely. So looking at the stress-based approach, the failure parameter clearly is the cross-section stress in the specimen. Looking at the fracture mechanics approach, the failure parameter is the local crack tip stress field, delta K. So let's go into the stress-based approach now. Here in this diagram, you see an overview what is happening. So again, we are doing the tests now on typical dumbbell specimens or rectangular specimens under tension or bending or what else. We load the specimen in a fatigue load, in this case a sinusoidal load with a maximum load, a minimum load, and the stress amplitude. And what we typically measure in conventional fatigue tests in materials and in polymers, that is the so-called Wöhler lines, the SN curves, where we measure the time, the cycle numbers to failure at different stress levels, at different amplitudes. So, and what you typically can find is such a curve, and sometimes for some materials you will even find a fatigue endurance limit. That is not the case for many polymers. So typically we do not find this fatigue endurance limit. And these Wöhler lines, then they can be evaluated based on typical diagrams in fatigue, like Smith diagrams or Hack diagrams, that they typically then show also and consider the R ratio effect in this. So the R ratio typically is the ratio between the minimum stress and the maximum stress in the test. So for these diagrams, a lot of tests, the different R ratios, of course, are necessary. And then there is even a possibility based on these SN diagrams and these Wöhler lines to calculate the fatigue life, to do a fatigue life modeling. And typically coming from metallic materials, this is done based on typical damage accumulation theories, like the Ball-Green minor rule, where the damage is accumulated at the different testing levels. And in the end, you can really assess the lifetime, not only of specimens, but of course also of components. And in the end, I will also show you one case study dealing with this aspect for polymers and short fiber reinforced polymers. But this is the conventional aspect of dealing with fatigue in metals and materials. If you want to get out more information of the test, and not only the cycle numbers to failure at different stress levels, you have to measure the hysteresis. So you have to measure the strain during the test. So this is again the stress. How does the specimen test is controlled, and you measure the strains. And if you plot then stress over strain, you get typically then the hysteresis at the defined cycle numbers. And of course, you can measure these hysteresis at different cycle numbers and compare the hysteresis. So looking at that, how can we now define such a hysteresis and the change of the hysteresis? We can typically do this by using two moduli. On the one hand, we can calculate the dynamic modulus, you can see here. And on the other hand, we can calculate the so-called second modulus. You can hear from the origin of the system. And if you compare now the hysteresis as a function of the cycle number, you typically will see that this hysteresis change. On the one hand, they can go to the right. This is typically also specifically a result of viscoelasticity and creep effects, and also the slope of the hysteresis, they will change. And this typically then is the result of damage that happens in the material, in the polymer. And now if you then calculate now the moduli, the second modulus, and the dynamic modulus, you typically then can get such a diagram. You see here then the relative modulus as a function of the cycle number. And typically then the second modulus is always lower than the dynamic modulus because it covers creep and damage. And the dynamic modulus, based on the definition of the two moduli and the calculation of the moduli, only covers the change in the slope of the hysteresis. It does not cover the creep aspect of the polymers. So by comparing these two moduli, you can get an idea about the relation between cyclic creep and damage accumulation. So in all together, you get a lot of more information out of these of a cyclic test than the Wöhler line if you are able to measure strains and evaluate here the stiffness values. But still, you only get stiffness as a function of cycle number. It's only an restricted use as a material law, these data that you get. So in a next step, well, and this was specifically developed here in our group over the last years, we now talk about so-called isocyclic stress strain diagrams. What do I mean with it? So in this case, here in the isocyclic sigma max epsilon max diagram, we do a conventional fatigue test. We measure the strains. We measure the stresses. So the stress level is constant, for example, here in the test, and then we measure the strains as a function of the cycle number. And this, of course, is done in, for example, here in 4 different tests at 4 different stress levels, maximum stress levels. And we measure the change of epsilon max as a function of the cycle number. And then what we are interested in now is the situation after defined cycle numbers. So, for example, after 1000 cycles. So, and in order to get and transform this information, we transform this into a sigma max epsilon max diagram. So these 4 points are transformed here into this new diagram at the four different stress levels. And what we get then is a so-called isocyclic stress strain diagram. That means now we have really the stress strain behavior of the material after a defined cycle number. And then we can do this then at different cycle numbers. And what we get in the end then is as stress strain diagrams related to the sigma max value for the different cycle numbers. And typically at higher cycle numbers, of course, the values are decreasing. So the material is getting softer and softer as a result, as already mentioned, from viscoelasticity and from damage. And again, looking here at the sigma max epsilon max diagram, similar to the second modulus, this diagram covers viscoelasticity and damage. If we are plotting only the delta values, so the delta sigma delta epsilon values, only like the slope in the dynamic modulus, we only get information about the damage in the material. And by comparing again these 2 procedures, we really get an idea what if the polymer is more sensitive to viscoelasticity or more sensitive to material damage. And the big advantage of this isocyclic stress strain diagram, we really have a stress strain relationship that can also be used as a material law in the end for simulation procedures. So that was very quickly, really very quickly, a short introduction into conventional fatigue, stress-based fatigue in polymers. Now I want to give also to you a kind of case study that you see how this can work. We worked here in Leoben in projects together specifically with the automotive industry with short fiber reinforced thermoplastics. And what the goal was to really use also software tools that are used for metallic materials for polymers based on Wöhler lines, SN diagrams. So in the automotive industry, there exist fatigue software tools where the input parameter are then the Wöhler lines, the material behavior. Of course, this material behavior has to be discussed as a function of different effects like the stress concentrations, mean stress, temperature, and so on. Then you have the geometry and the local stresses. Based on that, you can do a FEM analysis. And you know the load history in the real components. And based on that, you do a conventional fatigue life calculation based on damage accumulation. So this is standard for metallic materials. And we have now tried to consider these for specifically short fiber reinforced polymers. And the most important aspect is if you work with short fiber reinforced polymers, of course, as a result of the production process, typically injection molding, of course, you get a distribution of the fiber orientation in the component. And of course, you have to know this. This you can simulate based on molding simulations, but it's not always very accurate. But in the end, it's the basis of our calculations. But you can check it based on CT analysis, so computer tomographic analysis, if this molding simulation is right. But based on that, you can do then really an anisotropic calculation. And the input parameters then we have implemented over the last years now are different affecting parameters like the stress gradient. So if you also have notches in your components, of course, the influence of the mean stress, of the R ratio, the fiber orientations as explained, of course, the temperature effects in the polymers. You do the test, the Wöhler lines at different temperatures, and of course, statistical influences. And for example, you can see here in this diagram here the effect of temperature and fiber orientation in the short fiber reinforced polymers. You can see here in black, in red, and in blue the effect of the temperature. So of course, if you do the test at higher temperatures, you get much earlier failure here in this. So you see here 120 degrees Celsius, 80 degrees Celsius, and 23 degrees Celsius. And what in addition you see here in this diagram, this is the failure curve here for a fiber distribution longitudinal. That means in the direction of the injection molding machine. So here you are testing the specimen in fiber orientation. That means, of course, you have much higher failure cycles as if you test transversal to the injection direction, because in this case then you have typically also 90-degree oriented fibers, and the failure cycles will be much lower. So you need all this information from these roller lines to go into the calculation procedures. And here, for example, also to show you that we also use this already for quite complex components. This is a so-called lens holder, and the material is polyethamide 30% glass fiber reinforced. Based on all the calculations after the experimental evaluation of our results, we get here a simulation, a fatigue simulation of the most critical areas. We found these two positions. Also, we did component tests, and we got a real good correlation between simulation and component tests. And then if you really compare then simulation with the component tests here in this diagram, you can see here the triangles. These are the outcomes of the component tests. And in red and the blue, you see the simulation. In red, here, this is really the simulation where the anisotropic behavior is considered. So here, the fiber orientation is considered in the calculation, and in blue, it's an isotropic calculation without considering the real fiber orientation. Did you see if you compare then the red curve with the triangles, there's quite a good matching between component behavior and simulation. So that's it. Only finally now to the fracture mechanics approach here. Andy Bruno will go on in the next presentation in looking at composites, and you also heard about it during the day. So we have fatigue loads. And the most important aspect then going into fracture mechanics, we are measured then the crack growth as a function of the cycle number. We have then here the crack growth rate as a function of the K value or the G value. And what you typically see in a double logarithmic diagram is that you get the so-called Paris plots here. And with these Paris plots, you can do on the one hand material comparison, but on the other hand, what is also possible is to really do lifetime calculations. So you can integrate the Paris plot as from an initial defect to the thickness of a component or thickness of a specimen, and get the lifetime for the propagation of the crack. But you also have to consider, of course, the cycle number until a crack initiates. So you need a material law for that. And by the addition, the summation of these two parts, you get then a failure time for fracture mechanics fatigue applications. So that's it, a quick overview about fatigue. So you have additional information with more case studies I have uploaded. You can check it. And of course, if you need any more information, you can directly contact me. Okay, thank you very much.